I want to discuss with you an RLC circuit that is not so conventional. It's not a series circuit, but it is a parallel circuit. It is trivial, it's very pedestrian, but I hope you will learn something from that. I have here some driving voltage source, E0 cosine omega t. Let there be here a capacitor, C. Here a self-inductance, L. And here a resistance, R. Very different from the circuits that we have seen before, because they're not in series, but they are parallel. I always, when I solve these problems, take a moment that this is plus and that this is minus, and I make the assumption that there are no charges anywhere on the capacitor. This is always correct because my sign convention comes always out okay. That means this side of the capacitor will then be charged positive, and I get an E field in the capacitor in this direction. The E field in the voltage source goes from plus to minus, so it goes in this direction. There is no E field here, and there is an E field in the resistor in this direction. There is a total current going like this, and the total current will split into one current which goes through the capacitor, one current that goes through the self-inductor, and one current that goes through the resistor. So at any moment in time, the total current at any moment in time must be IC plus IL plus IR. At any moment in time. So I put a little t here, a little t here, a little t here, a little t here. I assume that no charge can pile up at any of these intersections, so therefore the total current that flows in here must be the total current that flows out here. It's the sum of these three currents. I will only solve for steady state solutions, and so I immediately turn to Faraday's law, the closed loop integral of E dot dl, and I do that for 3 loops. Now follow me closely. I'm first going to do it clockwise in this loop. I call that loop number 1. Then I'm going to do it clockwise in this loop. I call that number 2. And then I'm going to do it clockwise in this loop. I call that number 3. And for number 1 and for number 3, Kirchhoff's law holds. It is a non-conservative E field, so this equals 0. But for loop number 2, Kirchhoff's law does not hold. We have a non-conservative E field, and the answer is minus L dIL dt. So I can write down now, if I want to, the differential equations for these 3 loops. I start here, I go up against the electric field, so I get minus E0 cosine omega t. This is for loop 1. Then I go across the capacitor, so I get the charge on the capacitor divided by C. That's the integral of E dot dl through this gap, and that must be 0. And I keep in mind that dqc dt is the current through the capacitor. For loop number 2, I have minus E0 cosine omega t. When I go through here, when I go through the self-inductor, there is no electric field, so that component equals 0. I close the loop, and Faraday's law tells me that that is L dIL dt. So I can change these minus signs into plus signs. And then for loop number 3, I get minus E0 cosine omega t plus IR times R equals 0. That is, again, if you want to call it, Kirchhoff's law. And the total current at any moment in time is the sum of these individual ones. This is total plus IL plus IR, and that must be I0 cosine omega t minus some phase angle phi. And this holds for any moment in time, namely for this moment in time. If you want to, you can replace all these things by currents. In this case, it's easy. You take the first derivative of this equation, and so you find the current through the capacitor at any moment in time, which is dq dt, which would become minus c E0 omega sine omega t. The current through the self-inductor at any moment in time would become E0 divided by omega times the sine omega t. If you execute this integral, you will immediately see that. It's true that there could be some constant here, integration constant, but that would be a DC component, and that would certainly not be valid here. Then we have the current through the resistor at any moment in time equals E0 cosine omega t divided by R. So what do we have here now? We have a minus sine omega t, we have a plus sine omega t, and we have a cosine omega t. And so that's telling you that there are phase lags between these three currents. If I try to be a little bit pedestrian, almost high school-like, but we have time for that, and I, without wanting to insult you, I draw here a cosine term. So this is the driving voltage, a cosine term. And if I draw here a sine term, so this is the plus sine term, and the plus sine term holds for the self-inductor, so I put a self-inductor here, which is my shorthand notation. And if I put in minus sine omega t, minus the sine, which is the one that holds for the capacitor, then you see immediately, when you look at this point and this point, that the current in the capacitor is 90 degrees ahead of the voltage, which is nothing new. And you see here that the voltage driver is 90 degrees ahead of the current in the self-inductor. The current in the self-inductor is lagging. We have mentioned that before, because the self-inductor has the ability to quiet down the current. It doesn't like the current to come up, so the current will be lagging. And you see that very clearly in these curves, and you see that very clearly in the minus sine omega t, the plus sine omega t, and the cosine omega t. And therefore, this problem is screaming for a phasor diagram. A phasor diagram will tell me all the answers. I have here a vector I0R, this is the amplitude of the current, which equals E0 divided by R. This one rotates around with angular velocity omega. At this moment it has a positive value. When it is here, a quarter of a oscillation later, the projection on this axis is 0 and there is no current going through the resistor. When it is here, the current is going through the resistor but in the opposite direction. When it is here, there is no current going through the resistor, and when it is here, it's going through the resistor again in the same direction. So the current through the resistor, which is no surprise, is oscillating back and forth, and there are moments that it is 0. Now I put here in the vector the current, amplitude current for the capacitor, which is E0 omega c. You can see that immediately from my previous text, if I can find my previous text. Oh, it's somewhere on the floor, so I can't find it, but if you go back, you will see that this was the amplitude of the current when I took the when I derive the currents from these differential equations. And of course, this one also goes around with angular velocity omega. At this moment in time, the projection is 0, but when it's here, it is maximum in one direction, and when it's here, it is a maximum in the other direction. And I0 going through the self-inductor equals E0 divided by omega L, which follows from what I just did only minutes ago. And this also goes around with angular velocity omega. And this whole system, these three spikes together are coupled, they all go around with angular velocity omega. So if I add this one to this one, I get here a vector E0 times omega c minus 1 divided omega L. And so the net vector, adding all these three currents together, and that's what I have to do, because in this case the current through the system is the sum of these three currents, and I add them now, so to speak, in a vectorial sense. Then this current I0, which is the amplitude, equals E0 times the square root of omega c 1 over omega L squared plus 1 over R squared. Be careful, this may look similar to the one you have seen in a series, but it is very different. And the angle of phi, the way we define that, follows immediately also from this phasor diagram. The tangent of phi equals omega c minus 1 over omega L divided by R. And of course you can clean that up a little bit if you want to. And I0 itself would then be E0 times this monster. And since E0 per definition equals I0 times the self-impedance Z equals 1 divided by this monster. Now comes the question, when is I0 a maximum? What I'm trying to drive at is, are there perhaps resonances like we have in an RLC circuit? Well, look at this result. When is I0 a maximum? It's immediately clear when R equals 0, because then this term goes to infinity. Well, that is immediately obvious. You didn't have to do such fancy differential equations. If R is 0, you short circuit this battery. And if this battery has no internal resistance, of course you get an infinite current. So that's totally trivial. That's something that you could have immediately predicted. So now let's assume that R is fixed. When now is I0 maximum? Well, now I0 is maximum when omega c minus 1 over omega L squared is a maximum. Because you see here in the phasor diagram, you see here this term and you see this term. So when this is a maximum, you expect I0 to be a maximum. When will that be? Well, it will be the case when L equals 0 and when when c equals infinity. So when L equals 0, I0 becomes infinity, and when c goes to infinity, then also I0 goes to infinity. Is that obvious? Of course that's obvious. If I have L0, then this is just a solid bar. It has no self-inductance, it has no resistance, so I'm short-circuiting the system. So I get an infinite current going through if this voltage source has no internal resistance. What happens if C is infinitely high? That's also a short circuit, because infinitely high C is like a lake, which is so large in area that when you put water in it, that it can take infinite amounts of water, but the water level doesn't rise. Or, to talk in more electric terms, the capacitor can take on any amount of charge, but the integral E dot dl across the gap, and you may want to call that the voltage over the capacitor, will then not change. So that effectively is also a short circuit here. It can take infinite amount of charge, and so the current that will flow through here is then also infinity. So all these wonderful differential equations leads us only to totally trivial answers that we could have predicted without any differential equations. But now suppose that R, L, and C are all three fixed. And now I want to ask you the question, is there a value for omega for which I0 is a maximum? Because I'm still interested to see whether somehow there is a resonance in this system. Well, that would be the case when omega c minus omega L squared is a maximum. Because again, I go back to my phasor diagram, R is a given, I can't change that. L and C are givens, I can't change that. But I can manipulate, I can massage omega to see whether I can make this a maximum. So some of you may be very clever and you may say, aha, I take the derivative of this and I make this equal to 0, and of course I will find a maximum value, no doubt. Well, why don't you do that? Let's do that together. We get 2 omega c minus 1 over omega L. I use the chain rule. Then I get here a c, and then I get here plus 1 over L omega squared, and that must be 0. I lose the 2, and I multiply this out. So I get omega c squared plus c divided by omega L minus c divided by omega L minus 1 divided by L squared omega to the third, and that is 0. And these two cancel out. And what do I find? I find that omega equals 1 over the square root of LC, if you solve this equation. And I say, aha! There is a resonance. But if I say that, I'm wrong. Because this is not a maximum, but it is a minimum. If you take the derivative of that function as a function of time and you make it equal to 0, you have a chance to find a maximum and you have a chance to find a minimum. And it is immediately obvious that this is a minimum, because look at this equation. When omega equals the square root of 1 over LC, this term has become 0. Well, that means this arrow will always be shorter. Or let me put it this way. This arrow, which is the one I have left, if this is 0, is always shorter than if this is not 0. Any value that I have in this vector that is non-zero will make the current larger. So the current will be a minimum when this one is 0, and I only have simply I0 through R is E0 through R. So you can look at the phasor diagram and convince yourself that when this is 0, you actually have a minimum in current. There is no resonance. And if you now were to make a plot of I0 as a function of omega, it would be very boring. When omega goes to 0, the current goes to infinity. And the reason why the current goes to infinity is, I need my phasor plot. When omega goes to 0, this value goes to infinity. So it is the L that is doing it. And then it goes through a minimum, and then again it goes to infinity, and that is the C that is doing it, because when omega goes to infinity, this value goes to infinity, and so the current goes to infinity. And then there is here this minimum. And this minimum is at E0 divided by R. And this minimum is when omega equals 1 over the square root of LC. So you've seen the whole thing now. This is a parallel circuit, behaves very differently, but still it's good to do this kind of an exercise. It builds up some confidence in how you deal with phasor diagrams, how you deal with differential equations, and more important for me, how you get totally trivial answers that you could have predicted anyhow.